Welcome to this explainer. We're standing right at the edge of an unprecedented shift, and today, we're taking a cinematic journey across the foremost mind-bending frontiers of modern technology. Across software engineering, physical robotics, quantum computing, and global cybersecurity, the rules of what is actually possible are being rewritten daily by breakthroughs happening in the world's top research labs. My goal today is to break down these incredibly complex innovations so you can see exactly where the future is headed. So, to really grasp this massive leap, we gotta ask a pretty dramatic question, one that bridges our physical limits and this wild new digital frontier. I mean, think about it. If artificial intelligence can rapidly construct entire interactive environments in seconds, what actually happens to reality? The boundaries of how we build and experience the world are completely redefined. And that brings us directly to our first major frontier, which is the evolution of software development itself. We are officially moving away from the past, where AI was, just a fancy autocomplete, to the present reality of agentic engineering. This isn't just about an AI suggesting your next line of code anymore. We're talking about fully autonomous systems capable of executing massive, multi-step workflows. And the hardware catching up to the software revolution? It's staggering. We're seeing stuff like Qualcomm's new Dragonfly data center roadmap. These are chips specifically engineered to handle the massive brainpower these autonomous agents actually require.
Platforms like AutoDev and AgentScope are completely shifting the paradigm here. AI agents are now handling complex engineering workflows entirely on their own. AutoDev is automating tasks inside secure, isolated digital environments, while AgentScope 1.0 provides this massive framework for tool-based interactions. And for us, the end users, we're seeing the rise of 24/7 personal AI agents, like Gemini Spark, which can seamlessly navigate your entire digital life under your direction. The scale of this automation is just breathtaking.
There's this brilliant quote from a Google research paper on industrial agentic engineering that really hits the nail on the head. It points out that engineers basically have to surrender their own quirky stylistic preferences. Instead of fixing syntax, coders are now debugging the actual tools and constraints of the agents. The paper notes that raw AI models are virtually useless without a heavy harness of tools and strict guardrails. So the whole job evolves. If the agent's code passes the automated tests, boom, it's accepted. You aren't writing the code anymore. You're managing the intelligence that writes the code.
Which brings us to a pretty intense cliffhanger. As agents like Gemini Spark navigate our digital lives 24/7, who is really in control? Managing a digital calendar is one thing, right? But what happens when we hand over the reins and this artificial intelligence starts interacting with the physical environment around us? This exact collision between the digital and the physical brings us to our second frontier. Back in the 2010s, robots were incredibly rigid. If they hit an unexpected obstacle, they'd simply stop, or worse, crash. But today, we are transitioning to world action models, where robots actually understand the physical space they inhabit. So the crucial concept to understand here is the world model, an AI architecture that can generate, predict, and understand the physics of interactive environments. Take DeepMind's Genie 3, for example. It's a general-purpose world model capable of generating an unprecedented diversity of interactive worlds entirely from scratch. Instead of engineers hard-coding the laws of physics into a machine, the AI is organically learning how gravity, friction, and object persistence work just by exploring and predicting these generated worlds. You can really see this intelligence in action with NVIDIA's Cosmos 3. It operates on this fascinating two-step process. First, the model is pre-trained to essentially imagine and understand the physical world. It learns what happens if a glass drops or how a door swings open. Step 2 is fine-tuning that model to actually act within that world. It's exactly how we humans learn, right? We understand our environment first, and then we figure out how to manipulate it. And this translates directly into embodied agents, like DeepMind's Sima 2 learning to play, reason, and act in 3D virtual worlds. And then you have NVIDIA's Isaac GR00, which provides the incredibly complex brainpower needed to deploy actual humanoid robots out into the real world. The gap between what a robot can simulate in a training environment and what it can flawlessly execute on a factory floor or in a hospital, that gap is rapidly closing. And that leaves us pondering a pretty massive question. When physical AI flawlessly bridges the digital and real world, where do we draw the line between simulation and reality? It's a crazy thought, and it perfectly sets the stage for the microscopic mysteries of our next frontier. Because to power these incredibly complex AI systems of the future, traditional silicon chips are eventually going to hit a wall. We need a fundamental shift in how we process information.
Entering our third frontier, the quantum computing leap, we see a stark contrast between classical computing limitations and the totally mind-bending potential of quantum spin qubits. Classical bits limit us to binary choices. It's a 1 or a 0. But quantum computing leverages the principles of quantum mechanics, allowing qubits to exist in multiple states simultaneously. This opens the door to processing massive datasets that would literally take classical supercomputers thousands of years to crack.
Now, to really grasp this leap, we have to talk about fault tolerance, which is the massive hurdle preventing the tech industry from achieving useful quantum mass production. Quantum states are incredibly fragile. A slight change in temperature or even a stray electromagnetic wave can cause noise that completely destroys the calculation. Overcoming this error rate is basically the holy grail of modern physics.
Well, NVIDIA recently made a massive breakthrough in reducing this exact noise. By using advanced AI to interpret errors on quantum processors, they just cut the error rate down by over 300 times. 300 times! They have fundamentally changed the math on how quickly we might actually reach stable, practical quantum computing.
The stakes here are so incredibly high that IBM has committed $50 million to the U.S. Genesis mission, pushing quantum-centric supercomputing to the absolute frontier of science. The goal here is nothing less than modeling the universe, discovering brand new materials at the atomic level, and solving the world's most complex computational bottlenecks. But as you might guess, this immense computational power invites a rather dark inquiry about our global vulnerabilities, which pulls us right into our final frontier. Because think about it, the exact same quantum power that could cure diseases could also, theoretically, shatter the encryption protocols that protect our banks, our power grids, and our personal data.
So our fourth and final frontier is cybersecurity in the AI era. We are moving away from slow, manual attacks to a terrifying new world of automated, AI-driven threats. Bad actors no longer need to manually write every line of malicious code or brute force passwords by hand. No, they're deploying the very same agentic AI we were just talking about, except they are weaponizing it.
Let's just rapid fire through the threats IBM's security intelligence team is currently tracking in this new threat matrix. We're seeing agentic ransomware that adapts to defenses on the fly. We're seeing prompt injections designed to secretly manipulate the AI assistants you use every single day. This highlights the absolute necessity of AI red teaming, using tools like GPT-RED to aggressively test and defend these systems before they're ever deployed to the public.
Now, amidst all these heavy global vulnerabilities, we have to pause for a surprising, kind of funny fact highlighted by the tech channel Fireship. That massive CrowdStrike crash we saw recently, it bizarrely managed to take down a clown website of all things. It's a slightly humorous but incredibly profound reminder of how deeply interconnected our digital infrastructure is today. A single point of failure in an enterprise security update can cause this digital butterfly effect that takes out the most unexpected corners of the internet.
Getting back to the serious implications, governments are literally scrambling to build entirely new digital defense systems. We're seeing things like the new post-quantum cryptography executive order designed specifically to protect our data from Q-Day, which is the theoretical date when quantum computers become powerful enough to break standard encryption. We simply can't wait for the threat to arrive. The architecture to defend against it has to be built right now.
And that brings us to the end of this explainer, with a final, provocative thought about our place in this rapidly accelerating future. As we deploy autonomous agents to code our software, instruct robots to physically navigate our world, harness quantum mechanics to scale computing, and fight AI-driven cyber wars, we really have to ask ourselves, in an era where machines handle the complexity of our entire world, where they write malware and manage your passwords, is human oversight our greatest defense, or is it our biggest vulnerability? I'll leave you to ponder what comes next in the world of technology and how we ultimately choose to wield these incredible tools.